Hmm. Yeah. All right. The last day of class. Again, reminder, no class Thursday. So today we're going to talk a bit about optimization, and then we will talk about L'Hopital's rule. Today's the 11th. You guys haven't talked about which one? Either one? Okay. Well, hopefully you'll see it tomorrow or Friday. It's definitely something that's supposed to be covered in 21A. So whether or not you see it in class tomorrow, you certainly want to see it in class today because you will need to use it at some point probably next quarter. Okay, cool. Well, then you'll have a preview. Let's do a little bit of optimization first, just so we can have a little bit more exposure. Again, well, we'll talk about the process as we go along here. So let's look at the following question. What are the dimensions of the largest, and we'll talk about that in a second, cylindrical can that can be made to have 24 pi square inches of surface area. Or phrased another way, 24 pi square inches of material. So when we say largest, what do we mean? We mean the most volume in this case. So typically, if it's a three-dimensional shape, the largest is the largest dimension it has. So we want to make the volume biggest. Whereas if we were talking about a two-dimensional shape, we make it largest by giving it the most area. So in this case, as in most cases, I'm going to start off by drawing a picture. So here's my cylindrical can. And we don't know any of its dimensions. We are trying to find its dimensions. So we're going to label the things we don't know with variables. With typical names, I'm going to call this the radius R, this the height H. Almost all the time, not all the time, but most of the time with these problems, you have some sort of thing you want to optimize or maximize or minimize, and some constraint. So what are we trying to optimize? Well, in this case, we want to maximize the volume. So the volume equation for a cylinder, it's going to be the base area, which is the area of the circle, times the height. Most of the time with these problems, when you're trying to optimize it, you're usually going to start off with a function of two variables, which is problematic, right? We only know how to maximize and minimize a function of one variable. So that's where the constraint comes into play. So our constraint is our limiting piece of information. In this case, it's that we want the surface area to be 24 pi inches squared. So our constraint is that the surface area is 24 pi. but we need an equation for the surface area. And I always feel like the cylinder one's kind of weird, but it's not that bad. So for a cylinder, the surface area is the area of the bottom circle plus the area of the top circle, which can be 2 pi r squared, and then the area of the around part, which I always imagine is like a roll of paper towels. So if you have a roll of paper towels and you have one paper towel that like goes all the way around, and you take it off, what kind of shape does it have? You could say square or rectangular. So the area of this around part, well, it's the base, which is the circumference of the circle, which is 2 pi r, times the height. So the area of the around part of the cylinder is 2 pi RH. And that's going to equal 24 pi. Then our job is to isolate one of the variables in the constraint equation. And usually your choice is to pick the easier one. So I point out that there's an R here and an R here. So isolating R is going to be a challenge. I should isolate H. So I'm going to say 2 pi RH is equal to 24 pi minus 2 pi r squared. Let's do something easy first. Divide both sides by 2 pi. Think that RH is equal to 12 minus r squared. And then divide both sides by r. Think that H is equal to, sure, let's just write it as 12 minus r squared multiplied by r. Now that we have H in terms of r, we can take that and we can plug that in to the thing we're trying to maximize. Plug in H equal to whatever it's equal to into our volume equal to pi r squared times H. So now we have the volume is equal to pi r squared times 12 minus r squared over r. A function of one variable. So often when we write this, we don't just write v, we write v of the variable that it's a function of. Not required, just worth noting. Now that we have the thing we're trying to maximize as a function of one variable, we can take the derivative set equal to 0, find our critical points. But before we do that, we should make it easier to differentiate. We can definitely, I don't really want to use the product rule and the quotient rule here. It'd be much more sensible to multiply this out. In fact, to cancel an r here and an r here and say we have pi times r times 12 minus r squared, or preferably pi times 12r minus r cubed. That's going to be much easier to differentiate and set equal to 0. So we're going to find the critical points, critical values. So our derivative is equal to pi times 12 minus 3r squared. We set that equal to 0. I would factor out a 3, so 3 pi times 4 minus r squared equal to 0. So it is worth noting that we're going to get 2 critical points here. But one of them doesn't really make sense. We're going to get r equal to positive 2 or r equal to negative 2. But I think it's obvious that r equal to negative 2 doesn't make sense. You can't have a cylinder with a negative radius. It might be worth kind of noting, pointing out that in the beginning of this problem, we should have probably limited ourselves in our domain. So our domain in the beginning, if we had that the surface area 2 pi r squared plus 2 pi RH equal to 24 pi, I think r can't be any bigger than the square root of 12. Because if you had a weird cylinder, and this is where things get a little bit dicey, but some people are like, well, if the height was 0, then 2 pi r squared would equal 24 pi, and r squared would equal 12, and r would equal the square root of 12. So that's kind of the biggest r could be. If r was any bigger than that, then your cylinder would have too much surface area. So you can kind of think about your domain here as r being between 0 and the square root of 12. We'll come back to that. I'm not just saying it to say it. There is a reason we're saying it. So we found our critical values. And usually after I find my critical value, I like to go back and ask the question or read what the question is asking for again. So I go back and look at the question. It says, what are the dimensions of the largest cylindrical can that can be made to have 24 pi inches squared of surface area? I found the R dimension, but do I actually know it's maximizing the volume? So here's what I'd say about this. Most of the time with optimization questions, the thing they're asking you to find is the thing you're going to find. Meaning if they're asking you to find the dimensions that maximize, the thing you find is going to maximize. If they're asking the dimensions to minimize, they're going to minimize. But technically, we're supposed to check. So you could check in one of three ways, depending on the problem. You could either say, well, I could use the second derivative test. So we're going to check if R equal to 2 inches actually maximizes the volume. So the second derivative, so here's our first derivative again right here. Our second derivative would be v prime 3 double prime of R equal to pi times 0 minus 6R. And then if you plug in 2, v double prime of 2 is pi times negative 12. Our second derivative is negative, which means the function is concave down, which means we have a maximum. So the second derivative being negative means we do have a maximum. So yes, R equals 2 maximizes the volume. Or you could have said, well, on my interval, on my domain from 0 to root 12, if I look at the critical value of 2 and see what my first derivative is doing. Now, here's what I would honestly do if I was doing this problem. Like, yeah, it's a maximum. Did I check the values? Sure. I definitely plugged in a value less than 2 and saw that the derivative was positive there and negative there. You saw me do it, right? 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 The thing is, if it's going to be what you know it's going to be, you can kind of fake it, right? I can pretend like I checked and say like, yeah, the function is totally increasing there, decreasing there, so I have a maximum of 2, even though I didn't really do the work. We can actually do it though, right? If you plug in 1, 12 minus 3 times 1 is positive. If you plug in something bigger than 2, like 3, 12 minus 3 times 9 is negative. So yeah, the derivative is positive here and negative there, meaning the function is increasing and decreasing, so we do have a maximum. And then the third way of doing this is using the extreme value theorem. It's checking so the extreme value theorem says if your function is on a closed interval, then the maximum has to occur either at a critical point or an endpoint. So you check the endpoint in the original function, you check the critical point in the original function, and then usually the endpoints give you like 0 volume. So the middle point gives you some non-zero volume, and that has to be the maximum. You could also have said, oh yeah, v of 0 is going to be pi times 0 squared times whatever h is, which is 0, and v of root 12 is going to give you pi times root 12 squared, and I think that's when h has to be 0. So since those endpoints both give you a volume of 0, v of 2 being positive must be the maximum. So I know it's kind of a lot to digest, but what I'm really saying is there's 2 or 3 ways you can check to see if something's a maximum. I would say it's usually easier. If it's easy to take the second derivative, that's often the best path to take. Is take the second derivative, test your critical point, see if it's a max or a min. If that's not an option or taking second derivative is kind of gross, one of these ways will usually work pretty well. You can only really use this last way though if the function is defined on a closed interval, and that's often not the case. So take that for what you will. We're still not done though. We showed it was a maximum, but we didn't finish answering the question because it said to find the dimensions plural. We found the radius, we still have to find the height. Usually that's the easy part though, because we usually have what the other thing is equal to in terms of the thing we found. So if the height is 12 minus r squared over r, and we know that r is equal to 2, then our radius is going to be 2 inches, and our height is going to be 12 minus 2 squared divided by 2, which is 12 minus 4 over 2, which is 4. So our radius is 2 inches, our height is 4 inches. I do always think it's kind of interesting, just from an actual visual perspective here, is that when you're maximizing the volume of a can and minimizing the surface, or given a set surface area, you're maximizing the volume, you're gonna get a can where the height is the same as the diameter. So like, you've ever been in the grocery store and you've seen like kind of the larger cans of like refried beans, most of those cans kind of are that shape where the diameter is pretty much the same as the height. And that's for a reason, right? They're trying to get the most volume in those cans for the least amount of surface area used. Questions? Comments? And we'll look at a couple more optimization, and then we will talk about L'Hopital's rule. So let's look at one that's a little different. What point on the function y equal to 8 over x is closest to 3, 0? So we're trying to maximize and minimize something here, but it hasn't been explicitly stated in the problem. Let's draw a picture. My function looks something like this. It's your usual kind of hyperbola shape, and there's stuff over here too. And then 3, 0 is like, maybe, I don't know, right? Sure. Like right about there. I don't know. So there's some point on this curve, maybe it's right about there, I don't actually know where it is, that's closest to the point 3, 0. I don't know what this point is. I'm going to call it x comma y. But if that point is closest, that means that the distance between these 2 points is minimized. So our real job here is to minimize the distance between the unknown point x comma y and the given point 3, 0. So we're trying to minimize the distance, which is the square root of x minus 3 squared plus y minus 0 squared. Here's something I would almost always say is going to be the case. I would always say, what you should do. Instead of minimizing the distance, minimize the square of the distance. So think about this. If you're trying to make this quantity as small as possible, you're going to try to make the stuff inside the square root as small as possible. So instead, minimize distance squared. You can always do this, and it makes the calculus easier. The derivative is less ugly. You don't have a 1 over a square root. So that's always the case. When you're trying to minimize distance, instead you want to minimize distance squared. And really the reason is because if you took the derivative of this, you just get like 1 over 2 root this times the derivative of the inside, and then you would end up setting the derivative of the inside equal to 0, which is exactly what we're going to do when we take this derivative and set it equal to 0, is set the derivative of the inside part equal to 0. It's really the same work either way. All right. But I still have a problem. My distance is in terms of x and y. And I need to have a function of one variable to be able to find the critical point. So what's our constraint here? Well, that point just isn't anywhere. That point has to be on the curve, meaning this point really has coordinates x comma 8 over x, because that y value has to equal 8 over whatever the x value is. So often when you're dealing with points like this, or closest points, the constraint's just the equation of the function. So we're really minimizing distance squared equal to x minus 3 squared plus 8 over x squared. And again, before differentiating, I would probably at least do one thing. I don't think I'd multiply x minus 3 squared, but I would rewrite 8 over x squared as 64 times x to the negative second. It seems easier to deal with. So now we're going to differentiate. Take the derivative of d squared, going to equal 2 times x minus 3 minus 2 times 64 is 128 x to the negative third. Set that equal to 0. That's kind of gross. Let's see what we can do here. So 2 times x minus 3. I'm going to bring that over to the other side, so it's equal to 128 over x cubed. Multiply both sides by x cubed. X cubed times x minus 3. Divide both sides by 2 plus 2. Yeah, yeesh. X to the fourth minus 3x cubed minus 64 equals 0. It doesn't seem great. We kind of have to guess. So I point out, we have a limited range of answers for our guesses, right? Like we'll certainly have to be bigger than 0, right? X can't be 0. And right, we're probably not going to be super far away from 3. Also, a rational zeros theorem says that if you're solving a polynomial and it's going to be like a nice number, it has to be a factor of 64 or whatever that constant term over there is. So we can guess like 1, 2, 4, 8, 16. I feel like 4 is probably a good guess. 4 seems close to 3. It looks like it might be good for a picture. Let's try plugging in 4 and see what happens. If you get x equal to 4, see 4 to the fourth minus 3 times 4 cubed minus another 4 cubed. Oh, 3 times 4 cubed and another 4 cubed is 4 times 4 cubed, which is 4 to the fourth. That does equal 0. I know it's not the best method of solving an equation, but sometimes you just have to guess the answer. I'm curious if there's anything else. Yeah. Yeah, interesting. So here's where we couldn't use the extreme value theorem to see if the maximum, because our interval of what x can be is from 0 exclusive, right? We can't plug in 0 all the way to infinity. So looking at our one critical value here, we pick a number less than 4 to plug into our derivative, like, I don't know, 1. It's going to be negative 2 minus 128 over 1. And that's pretty negative. Pick something bigger than 4, like a billion. This is the big number. 2 times a billion minus 3 is pretty big. Minus 128 over a billion cubed is very small. That's going to be very positive. So yes, my function is decreasing left of 4. It's increasing right of 4, meaning we have to have a minimum when x is equal to 4. So we've minimized that distance, which means the value we found is the closest. Well, let's just say the value for x, we still haven't answered the question. Right? The question says, what point is closest? So we have to take our x value of 4, plug it back into this here to find the corresponding y coordinate. So if x is 4, y is going to equal 8 divided by 4, which is 2. So the closest point is 4, 2. Yeah. By playing it back into the constraint. But I would say more generally, whenever you're trying to find like the other thing, whether it's like the height or the other dimension of volume or the other thing you're looking for, you've almost always by that point somewhere written an equation for that thing. Like in our previous problem, we'd found the radius and we were then trying to find the height, and we already had written height as an equation in terms of the radius. So usually that expression that makes it easy to find the other piece is already in your work somewhere. Yeah. So that's in this problem, that was not explained very well because we just kind of guessed it. Most of the time with these problems, we're not solving a 4th degree equation equal to 0. And so usually it's just like a quadratic and we factor it, or there's some lesser word. Here, we really said, well, our answer has to be a factor of 64 if it's going to be a nice number. And then we did just say, well, 4 seems like a likely answer, and we plugged it in and got it. But you're right, we didn't really show explicitly how you solve that, and it's not something you can really do actually. So yeah, not a very satisfying answer, I'm aware. Sometimes you have to guess. Not a lot. Okay. Let's see. Is there one? I feel like there was one other one I really wanted to go to. No, none of those. All right. Yeah, let's do that one. Okay. The last optimization problem, and then we will talk about some L'Hopital's rule. Find the area of the largest isosceles triangle sorry, that's not. I realize this question is not. I'm thinking of thinking of a different picture. Let's try that again. Apologies. Find the volume of the largest cone that can be inscribed, fit into in a sphere of radius 6 inches. So there's two pictures we're going to draw here. One of them not very helpful. So here's the picture of what's actually happening. We've got a sphere, got a radius of 6 inches, and then we're inscribing inside of it a cone. Where's my pen's going? Okay. There's my cone. But that picture doesn't really help us a lot. It's much more useful to draw a circle with a triangle inscribed in, because that's kind of the meaningful part. I will point out that our cone, right, this is the radius of our cone, which is not 6, right? It's much smaller than 6. And here's the height of our cone, which better be less than 12 because the diameter of the sphere is 12. But the picture we actually really want is this picture here. We just got a circle, and then we're going to draw our quote unquote cone like this. All right. So usually when you're drawing things like this, it makes sense to center them at the origin. So like I want the center of my circle to be where the origin is. And then usually, well, actually, let's just kind of write out what we're going to do here. So we want to maximize the volume of the cone. The volume of a cone, the formula is 1/3 pi r squared times h. It's the same as the volume of a cylinder with the same base, radius, and height, just a third of it. In fact, if you ever take, like, I remember in chemistry class when I was in high school, like my teacher had like a cone and a cylinder with the same base and rate or same radius and height. And you could like fill up the cone with water 3 times and put it into the cylinder and it was perfect. Like it was kind of cool to see that it actually was the right amount of volume. Anyway, we want to maximize this. And as usual, we have more variables than we can handle. We have radius and height. So we need to eliminate one of these variables through a constraint. The constraint here is not super obvious. So here's what I would say. When you have shapes inscribed in each other, you kind of want to draw a segment from the center to where the shapes touch each other. So I want to draw that right there, where the circle and the triangle touch, or where the cone and the sphere touch. Not to here, because that just feels too obvious. We want to draw that. And we know that that length, being the radius of the sphere, has to be 6. We also know that this length here is the radius of our cone, and that this length here, well, I know that this length here is the height of the cone, and that this length here is also the radius of the sphere, which is 6. So it looks like this length here is the height minus 6. And now I have a right triangle and I can make an equation relating the radius and the height. So my constraint here, which is a little bit weird to come by, is that your radius squared plus h minus 6 squared is equal to 6 squared. And now we have to ask ourselves, which thing do we want to solve for? We want to solve for r or for h? Well, actually, kind of neither. What I really want to do is solve for r squared. So I already have r squared almost all by itself already. Check it out. R squared is 6 squared minus h minus 6 squared. And you can just replace the entirety of r squared with this here, which we could even simplify. Right, this simplifies pretty nicely. It's 36 minus h squared minus 12h plus 36. The 36's cancel, and you get negative h squared plus 12h. I'm not even going to take the square root of it. Fine, I'll take the square root of both sides. R is the square root of negative h squared plus 12h, but I don't really need that for right here. Because now my volume equation as a function of height is going to be 1/3 times pi times r squared, which is negative h squared plus 12h times h. I'm just replacing the r squared with what r squared is equal to. We could have gone the other direction. It would have been less nice. If we had solved for h instead, we would have had like h minus 6 squared equal to 6 squared minus r squared, and then square root of both sides. H minus 6 equals the square root of 36 minus r squared, and then added 6. That seems much less nice to then plug into that equation and take the derivative of r squared times 6 plus the square root of 36. That seems terrible. So usually you want to try to pick the thing to solve for that seems easier. And sometimes it's not always obvious, but if one path seems like it's getting really dicey, it might be good to try the other way. So then I'm going to multiply the h through. When you're trying to simplify the thing you're going to differentiate, any constant multiples we can just leave out in front. So that pi over 3 just hangs out. But the h I want to distribute so I don't have to use the product rule. We've got negative h cubed plus 12h squared. Now we can take the derivative. The derivative is going to be the pi over 3 still hangs out. I get negative 3h squared plus 24h. Set that equal to 0. Factor out a negative 3h. You get pi over 3 times negative 3h times h minus 8 equal to 0. So it looks like our critical values are either h equal to 0, which probably isn't going to produce a very voluminous cone if it's got 0 height, or h equal to 8. We can check to see if it maximizes. Again, I would recommend the second derivative test here. Take the second derivative. V double prime of 8 is going to be, well, I should have found V double prime first before I just plugged in an 8 there. V double prime is going to be pi over 3 times negative 6h plus 24. And if you plug in 8, V double prime of 8 is going to be pi over 3 times negative 6 times 8 plus 24, which is for sure negative, meaning we're concave down, meaning we have a maximum. So yes, h equal to 8 maximizes the volume. And now we have to ask ourselves again the question, what are we being asked to do in the first place? Did they say find the dimensions? Did they say find the volume? Did they say something else? Let's see. Find the volume of the largest cone. I would point out that even though they say find the volume, I would still probably like to find the radius because it just feels good. But we technically don't have to. If we just want to find the volume, you can take that 8, plug it back into your volume equation where you just have the height, and that would be good to go. So to answer the question here, the volume, the max volume would be V of 8, which would be pi over 3 times negative 8 cubed plus 12 times 8 squared. which would be pi over 3 times, let's see, we factor out an 8 squared. We're left with negative 8 plus 12. That's 4 times 64, which is 256. So you get 256 pi over 3. I would also want to know what the dimensions were, though. So I'll point out that the radius, which is the square root of negative h squared plus 12h, is equal to the square root of negative 8 squared plus 12 times 8, which is the square root of 32. So there's our dimensions of our cone with maximum volume and the maximum volume of that cone. So even though these problems are all very different, they all still have the same hallmarks, right? We're finding the thing we're trying to maximize or minimize. We're finding a constraint. We're isolating one variable in the constraint, plugging that into the thing we want to maximize to get a function of one variable, finding the derivative, setting it equal to 0, finding critical points, checking to make sure they give us a max or a min, even though we kind of get it about doing that. And then finally, finding the thing the question actually asks. It's a lot of steps, but they're each doable. And while I would love to say more about that, we should talk about L'Hopital's rule. Oh, question, yeah. Yes. So over here, so in the previous step, our first derivative was, let me remind myself what it was here. Our first derivative was pi over 3 times negative 3h squared plus 24h. So here's what we're saying when we do the second derivative test specifically. We set this equal to 0, and we ended up factoring, I factored out a negative 3h and had h minus 8. And setting that equal to 0, we're getting either h equal to 8 or h equal to 0. And what's happening is we know that at h equal to 8, we have kind of one of three things happening. Either at 8, the function looks like this because the derivative is 0, or at 8, the function looks like this because the derivative is 0, or maybe at 8, the function looks, unfortunately, like this, where you either essentially have a maximum or a minimum or an inflection point. And the way we check to see which of those we might have is by using the second derivative. So we say, okay, the second derivative is, let's see, I'm just going to leave the pi over 3 out in front here. The derivative of the inside is negative 6h plus 24. And then I'm going to plug in 8, my critical point. Say, okay, if I plug in 8, getting pi over 3 times negative 6 times 8 plus 24, that's negative 48 plus 24, which is, I didn't actually do the calculation, I just said it was negative, but I know I'm getting negative 24 divided by 3 is negative 8 pi. I don't actually care about the value, I just care that it's negative. If it's negative, that means that V is concave down, meaning it looks like this, meaning we have to have a maximum because the function is concave down. Concave down means max. If the second derivative is easy to do, especially if you've got like a polynomial, I really, really think it's the best way to check your critical point to see if it's giving you what you've got. Again, this is all based on the assumption that your teacher is going to require you to check that your thing is what it is and not just finding the null. That's probably a detail we might have been able to gloss over, but it feels unethical. In real life, you should check to make sure that your critical points give you a maximum if you're trying to maximize something, or give you a minimum if you're trying to minimize something. There are stories of people not checking and accidentally building things that had very, very small wings instead of very, very large wings. So just make sure you check your things. Let's talk about L'Hopital's rule. So here's the gist. Here's the rule, actually. So the rule, if your limit as x approaches whatever it's approaching of some quotient, it must be a quotient. If it is anything else, you cannot use L'Hopital's rule until you rewrite it to look like a quotient, meaning a fraction. If that limit is either a 0 over 0 type or some sort of infinity over some sort of infinity, the sorts do not have to match. You can have a positive on top and a negative on bottom or vice versa. Then it is true that the limit as x approaches a of f over g is equal to the limit as x approaches a of the derivative of f over the derivative of g. That's what L'Hopital's rule says. If you have an indeterminate form, it's 0 over 0 or infinity over infinity, you can take not the derivative, but the derivative of the top and the derivative of the bottom and take the limit of that and get the same result. Some examples you might be familiar with. The limit as x approaches 0 of sine of x over x. We've seen this one a fair amount in the beginning of the quarter. That limit was 1. But now we can use L'Hopital's rule. Oh, by the way, when I use L'Hopital's rule, I think it's a good idea to write L apostrophe H above the equal sign. It's pretty typical notation for showing someone that you're using L'Hopital's rule. We still have to write the limit. But then we take the derivative of the top, which is cosine of x, the derivative of the bottom, which is 1, and then we can plug in the 0 and get cosine of 0 divided by 1, which is 1 divided by 1, which is 1, which we already knew, but it's nice to see it appear another way. Or another example might be something like the limit as x approaches 3 of x squared minus 5x plus 6 over x squared minus 9. If we plugged in 3, we'd get 0 divided by 0. Indeterminate form. We could factor and cancel, right? One way of doing this is to say, yeah, I can factor the top. It's going to be x minus 3 times x minus 2. I can factor the denominator, x minus 3 times x plus 3. The x minus 3's cancel. I can plug in 3 for the remaining x's and get 3 minus 2 over 3 plus 3, which is 1 over 6. Or we could use L'Hopital's rule and said this is also equal to the limit as x approaches 3 of derivative of the top is 2x minus 5. Derivative of the bottom is 2x. And now if I plug in 3, look what I get. I get 2 times 3 minus 5 over 2 times 3, which is also 1 over 6. So for some limits that we've done before, we could also now use L'Hopital's rule instead. I'm going to give you one more. The limit as x approaches infinity of 5x squared plus 7x plus 1 over 9x squared minus 3x minus 4. Before you might have just said that this limit was equal to 5/9 because it's a limit to infinity and the degree on top and the degree on the bottom are the same. So it's the quotient of the leading coefficients. But this is an infinity over infinity type. And instead of doing that shortcut or dividing the top and bottom by x squared, which is also right, that's how we would usually actually show the work there, is you would divide the top and bottom by x squared and say you had 5 plus 7 over x plus 1 over x squared, and then on the bottom 9 minus 3 over x minus 4 over x squared. And then all those things being divided by something getting large get really small. But we could also use L'Hopital's rule. Say we have the limit as x goes to infinity of the derivative of the top, which is 10x plus 7, over the derivative of the bottom, which is 18x minus 3, which is still an infinity over infinity type. So we use L'Hopital's rule again. You can get the limit as x goes to infinity of the derivative of 10x plus 7, which is 10, over the derivative of 18x minus 3, which is 18. And then the limit of a constant is just the constant. And 10 over 18 is equal to 5 over 9. And if we could only use L'Hopital's rule for limits we already knew how to do, what would be the point? There's lots of limits where you can't just evaluate them in ways we know. You kind of have to use L'Hopital's rule. Let's look at some examples where we can't just do it this way. For example, the limit as x goes to infinity of x cubed divided by e to the x. So certainly both the top and the bottom of this limit are getting infinitely large. X cubed is getting infinitely large. E to the x is getting infinitely large. I'll remind you, when we have an indeterminate form, the answer can literally be anything. It's often going to be 0 or infinity, but that doesn't mean that sometimes it's going to be 5 or 3 or 17. So just be on the lookout, right? Anything can happen. But we're going to start using L'Hopital's rule. And here's kind of the process. You use L'Hopital's rule one time. You say, okay, great. Limit is x goes to infinity. You still have to write the limit every time. Derivative of the top is 3x squared. The derivative of the bottom is e to the x. I don't actually want to plug it in right now. I just want to think about what would happen if I plugged in. If I plugged in infinity, I would still get infinity over infinity, which is still the same sort of indeterminate form, so I'm going to do it again. So we use L'Hopital's rule again. We get the limit as x goes to infinity of 6x is the derivative of 3x squared, e to the x is the derivative of e to the x. We still have infinity over infinity, so we do it again for the last time. And we get the limit as x goes to infinity of the derivative of 6x is 6. The derivative of e to the x is still e to the x. But now we don't have an infinity over infinity. We have 6 divided by infinity, which is going to be really, really small. In a similar way, you could argue that x to any power divided by e to the x, its limit would eventually be 0. So just as a kind of interesting point, for any n that's greater than 0, the limit as x goes to infinity of x to the n divided by e to the x will eventually be 0 if you use L'Hopital's rule enough times. Because the bottom derivative is just going to stay as e to the x every step, and the derivative of the top is going the power is going to reduce by 1 every single time until you get down to something that's going to be a constant. Which shows you that exponential functions always overpower power functions. So another way, what this also says is that e to the x is bigger than x to the n for any n eventually. A few more examples here. What about the limit as x approaches infinity of the cube root of x over the natural log of x? First of all, is it even the right type? So it's really important when you're looking at limits like this, before you just throw L'Hopital's rule at it, you have to make sure you're allowed to. So is it a 0 over 0 or is it an infinity over infinity? Well, yeah, here it's an infinity over infinity because the cube root of x certainly gets infinitely large as x gets infinitely large, and natural log of x also gets infinitely large as x gets infinitely large. Think about the graphs of them. Even though they kind of, right, they don't get big fast, or they kind of, I wouldn't say flatten out, but they start to kind of slow down. They're concave down. They still do get larger and larger and larger and larger and larger without bound. So both the cube root of x and the natural log of x both keep getting larger and larger. So they do get infinitely large, just very slowly. Okay, so we can throw L'Hopital's rule at it. All right, so I might have been better off writing that as x to the 1/3. The derivative of x to the 1/3 is 1/3 x to the negative 2/3. Derivative of natural log of x is 1 over x. This is where it's important to be careful. If I was not careful, I might do the following. I might rewrite this as the limit as x goes to infinity of 1 over 3x to the 2/3 power over 1 over x, which isn't bad as a first step. But if I stop there and then try to say, well, what's happening if I plug in infinity? I've got 1 over something big, which is 0, over 1 over something big, which is 0. It's like I have a 0 over 0. And I could then make the argument that, well, it's 0 over 0, so I should use L'Hopital's rule again. I should not use L'Hopital's rule again, because I can simplify this further. So we want to try and simplify these expressions as much as is reasonable, which I know is not very specific, but it's just kind of like do it until it makes sense not to. I'm going to simplify this and get the limit as x goes to infinity of 1 over 3 times x to the 2/3 times x over 1. And then x over x to the 2/3 simplifies as x to the 1/3 power. So it's really equal to the limit as x goes to infinity of 1/3 times x to the 1/3. And then it's just getting bigger and bigger and bigger. As x is really, really big, the cube root of x also gets really, really big. So this limit is infinity. Which never feels like a winning answer, but it is the answer. Again, from a which kind of function is bigger perspective, this means that the cube root of x is much, much bigger than the natural log of x eventually, even though they don't look that different in the beginning here. It's true actually for any root of x. 4th root, 5th root, 6th root, et cetera, et cetera, et cetera. All those will eventually outpace a logarithmic function. Logarithmic functions are kind of the ones that grow the slowest. Everything else usually grows faster. Every other kind of typical function grows faster. Let's take a look at some more examples. Here's a funky one. The limit as x goes to 0 of 2 to the x minus 1 over 3 to the sine of x minus 1. So we do need to check that we can use L'Hopital's rule before we just do it. So if we plug in 0, we get 2 to the 0 minus 1 over 3 to the sine of 0 minus 1. Sorry, sine of 0 minus 1. That's 1 minus 1 over sine of 0 is 0. 3 to the 0 is 1. Yep, that's a 0 over 0. So L'Hopital's rule. All right, I know it's been a minute. Who remembers what the derivative of 2 to the x is? Ugh. It's 2 to the x times the natural log of 2. Just like the derivative of e to the x is e to the x times the natural log of e. Or the derivative of b to the x is b to the x times the natural log of the base. And if your exponent is more complicated, there's a chain rule in there. The derivative of 3 to the stuff is going to be 3 to the stuff times the natural log of 3, also times the derivative of the stuff, which is cosine of x. This is where it's really easy to convince yourself to just keep going, but we don't. Every time, immediately after applying L'Hopital's rule, you should try plugging in when x is approaching. Every time. Maybe I don't always write it down, but I'm always thinking, okay, if I plugged in x approaching 0 or infinity, what happens? So we plug in 0, I get 2 to the 0 times natural log of 2 over 3 to the sine of 0, which is 0, times natural log of 3 times cosine of 0, which is 1. That's definitely not an indeterminate form. That's going to be 1 times natural log of 2 over 1 times natural log of 3 times 1. So that's what the limit is. The natural log of 2 divided by the natural log of 3. Kind of interesting. Sure. Sore from writing all quarter. So let's look at this next one here. Oh yeah, this one's a good one. The limit as x approaches 0 of sine of x minus x divided by x cubed. And as you might have guessed, you plug in 0, we're going to get 0 over 0. You should make sure you check though, because occasionally someone's going to write a tricky one where like the top is 0 and the bottom isn't 0. And then people will start throwing all kinds of things at it when you could have just plugged in your number and gotten like 0 divided by 5, which is 0. It doesn't always happen, but occasionally someone tries to be kind of slick about it and tries to do that. Just make sure you check. But here, if we plug in 0, we see we get 0 minus 0 over 0. So L'Hopital's rule. L'Hopital's rule it is. So, derivative of the top is cosine of x minus 1. The derivative of the bottom is 3x squared And if we plug in 0, we're going to get 1 minus 1 over 0, which is another 0 over 0. So we're going to do it again. Derivative of cosine of x is negative sine of x. Derivative of 3x squared is 6x. Unsurprisingly, we still get 0 over 0. So we do it again. You keep doing it until you get a not 0 over 0. So the derivative of sine of x, or sorry, derivative of negative sine of x is negative cosine of x. Derivative of 6x is 6. We know for sure we're not going to get 0 over 0 this time. Plug in 0, you get negative cosine of 0 divided by 6. If it were me and I couldn't remember what cosine of 0 was, well, I probably have problems before this, but like I would write this step in case I was like having a problem and then be like, okay, then it's going to be negative 1 over 6. But that shows you at least know that that's the place where you're supposed to plug it in. Okay. So if you've got something that's already rational, that's not right, a quotient, some top divided by some bottom, check to see if it's 0 over 0 or infinity over infinity. But sometimes we're not going to have that. We have to do the work of writing it like a quotient before we can use L'Hopital's rule. So there's like 5 other types of indeterminate forms. So other indeterminate forms. I should say other indeterminate forms that can be rewritten to look like a 0 over 0 or an infinity over infinity. And they are the following. Infinity times 0. So when we say infinity and 0, we don't mean those things. When I say infinity times 0, what I really mean is a really big number times a really small number. That's what we actually mean when we write this, but it's more convenient to write infinity times 0. So that's an indeterminate form. Infinity minus infinity. Infinity to the 0th power. 0 to the 0th power. And oh my gosh, what's the last one? Oh yeah, 1 to the infinitieth power. So again, we don't actually mean the number 1, we mean the number really close to 1. So if you have a number that's really, really close to 1 and you multiply it by itself a bunch of times, it might not end up being close to 1. It might get really, really big, or it might get really, really small, or something else that like it's unclear. The 0 to the 0 is also kind of wacky. Infinity to the 0 is all, these are all interesting cases. So let's look at a few of them. So let's look at this first. Let's say we have the limit as x approaches 0 from the right of x squared times the natural log of x. Is this one of these types? Well, let's see. Clearly, this is going to 0 here. What about the natural log of 0? This is where it's really good to have an idea of what the natural log of x function looks like in your mind. Think about what natural log of x looks like, which again, my hand's not great for this. And I feel like I might not have mentioned this already, but on your right hand, you have a pretty good, you probably all better, have a pretty good natural log of x function like right there, and an e to the x function like right there. On your right hand. Make sure you're looking at your right hand. E to the x kind of up there, natural log of x kind of right there. Natural log of x has a vertical asymptote. And so we can see that as x approaches 0, the natural log of x function gets more and more and more negative. So this is like a 0 times a negative infinity, which certainly qualifies as this type. But we can't use L'Hopital's rule because we don't have a fraction. And I can't tell you how many times I've seen people take this and like take the derivative of each part and try to use L'Hopital's rule. We can't do it that way. We have to write it as a fraction. So we're going to bring one of these two factors down to the denominator as its reciprocal. Usually you want to bring the easier thing to the denominator, which is never the natural log. So we want to rewrite this as the limit as x approaches 0 from the right of natural log of x divided by the reciprocal of x squared. Which, yeah, might be better to write as x to the negative second power so that it's easier to differentiate both the top and the bottom. So now we can use L'Hopital's rule. We've got Well, actually, I should point out we can use L'Hopital's rule. The top is still going to negative infinity, and 1 over 0 is getting positively infinitely large. So that bottom part is going to positive infinity. So we do have an infinity over infinity type, which means we're allowed to use L'Hopital's rule. And so when we use L'Hopital's rule, it's going to be the limit as x approaches 0 from the right. Derivative of the top is 1 over x. The derivative of the bottom is negative 2 times x to the negative third. And just like the previous one, we should simplify. So if I multiply the top and bottom by x cubed, I get the limit as x approaches 0 from the right of 1 over x times x cubed over negative 2, which is just the limit as x approaches 0 from the right of x squared over negative 2. Plug in 0 for x, and you get 0 divided by negative 2, which is 0. I would describe this as the 0 winning, right? You had the 0 times the negative infinity, and the 0 overpowered how big the infinity was to make this thing really small. That's not really necessary to say that, it's just how I think. Or the x squared approached 0 faster than the natural log approached negative infinity. Let's look at some other strange examples here. Yeah, sure. That's a good one. Actually, let's do something else. Yeah. So one example I'll just warn you about. Let's say we have the limit as x approaches 0 of, yeah. All right, 1 sec. Yeah, that's terrible. Sine cubed of 2x over x cubed. This problem is terrible. It is not a problem where we should use L'Hopital's rule, even though you could, right? This is a 0 over 0 type of limit. You can totally use L'Hopital's rule. And the first step isn't too bad. Again, thinking of this as sine of 2x quantity cubed, you might not want to write this down. You could rewrite this as the limit as x goes to 0, or I should say you could use L'Hopital's rule and get the derivative of the top, 3 times your stuff squared times the derivative of your stuff, which is cosine of 2x times 2, all over the bottom derivative, which is 3x squared. Still 0 over 0. Now, using L'Hopital's rule, the next step is going to get gross. Because not only do I have to use the chain rule, I also have to use the product rule. And it's still not going to be done after the next step. I have to use L'Hopital's rule 2 more times to get to the answer. This problem, you should definitely do the old way. The way where we thought of it as sine of something over the same something. So the better path here is to say, hey, wait a minute. I can write this as sine of 2x times sine of 2x times sine of 2x times something over x cubed, and then throw in a 2x there, a 2x there, a 2x there, and a 2x there, a 2x there, and a 2x there. And then each of these, their limit is 1, because it's sine of something over the same something going to 0. You get 1 times 1 times 1 times the x's cancel, and you get times 2 times 2 times 2, which is 8. Much, much, much easier than trying to use L'Hopital's rule the next 2 times in this problem. So sometimes problems, even though you can use L'Hopital's rule, it is not the best tool for the job. But sometimes it is. This next problem kind of made me think of that. The limit as x approaches infinity of x squared times sine of 1 over x squared. I'll point out this is also an infinity times 0 type. X squared is getting infinitely large. Sine of 1 over x squared is becoming sine of 0, which is getting closer and closer to 0. And in this case, we could totally rewrite it as the limit as x goes to infinity of sine of 1 over x squared over 1 over x squared. Which if you wanted to, you could probably justify or get away with just saying it's equal to 1. Because you recognize it's sine of a thing over the same thing, and the thing is getting closer and closer to 0. But you could also use L'Hopital's rule here, and it's not too terrible. It's going to be, check this out. The derivative of the top, which is cosine of our stuff times the derivative of our stuff over the derivative of the bottom. And I'm going to be extra special here and not even find the derivative of 1 over x squared because they're going to cancel. The derivative of 1 over x squared divided by the derivative of 1 over x squared is 1. And then I'm just taking the limit as x goes to infinity of cosine of 1 over x squared, which is cosine of 0, which is 1. A lot of times this happens where the top and bottom, you have the same derivative multiplying and they cancel out, which is kind of nice. All right. How much time is I got here? 13 minutes. Okay. Let's look at some of these other ones. Yeah, let's do that one. So a while ago, I think, I mentioned that the limit as h goes to 0 of 1 plus h to the 1 over h power was equal to e. Or something like that. Yeah, that looks right. I might have written it like this, or the limit as n goes to infinity of 1 plus 1 over n to the nth power was equal to e. And I didn't really offer any justification. I just kind of said it was true. I might have talked about how it comes from like some compound interest formula. But now we're actually going to show that this limit is equal to e. It's kind of neat. So we're going to do the limit as x goes to infinity of 1 plus 1 over x to the x. And I'll point out, this is definitely one of our 1 to the infinity types. There's two different ways of approaching this. Both are fine. I personally prefer to just rewrite this as the limit as x goes to infinity of e to the natural log of the thing you're trying to take the limit of. Other people just take the natural log, take the limit of that, and then undo the natural log at the end by saying it's e to whatever you've got. We'll do that. We'll do it the other way the second time. So now, the whole reason we've wanted to introduce the natural log here is so that we can get rid of this x in the exponent. So we're going to rewrite this as the limit as x goes to infinity of e to the x times the natural log of 1 plus 1 over x. And then we're going to rewrite this as the limit as x goes to infinity of, you can write e to the, your teacher might write exp. I feel like one of your teachers likes to write exp for e to the stuff a lot. We have e to the, I'm going to rewrite the x times the natural log of 1 plus 1 over x as the natural log of 1 plus 1 over x divided by the reciprocal of x. And now we have in the exponent there a 0 over 0 type. 1 over infinity goes to 0, 1 plus 0 is 1, natural log of 1 is 0, and 1 over infinity goes to 0. So this thing here, that is a 0 over 0 type. And usually we don't write it this way, but you could also make the step of saying the limit passes through the continuous function and saying the limit of e to the stuff is equal to e to the limit of that stuff. People usually skip writing this step, but you can write it. So this is equal to e to the limit of natural log of 1 plus 1 over x over 1 over x. And now finally, we can use L'Hopital's rule because this fraction is a 0 over 0 type. So we get e to the limit of the derivative of the top, which is 1 over 1 plus 1 over x, times the derivative of 1 over x. I think it's probably worth just memorizing the derivative of 1 over x is negative 1 over x squared. And the bottom, the derivative of 1 over x again, is negative 1 over x squared. The negative 1 over x squareds definitely cancel. And then the remaining 1 over x is going to go to 0 as x goes to infinity. So we're left with e to the 1 over 1 plus 0, which is e to the 1, which is e. It's kind of cool that this limit of 1 plus 1 over x to the x, as x gets really, really big, this expression gets closer and closer and closer to e. More generally, the limit as x goes to infinity of 1 plus k over x to the x power is going to equal e to the k. And maybe you can kind of see if I just threw in a k where that 1 was in each of these spots, k there, k there, k there, k there, k there, k there, k there. We'd have a k right there, and then you'd have a k over 1 instead of just a 1. So that changes it just a little bit. Let's do another one where it's a little bit different. So let's look at yellow. So this is the way I prefer to do it because I feel like it's less like writing, rewriting. But let me show you how other people approach a problem of a similar nature. Let's say we want to find the limit as x approaches 0 from the right of sine of x to the 1 over x. What some people prefer to do is they prefer to take the natural log of the expression first. So instead, we're going to say, we're going to let yeah, sure. We're going to let y equal the natural log of sine of x to the 1 over x. And then note that e to the y is equal to e to the natural log of sine of x to 1 over x, which is just sine of x to 1 over x. But then we're going to deal with this. So the limit as x approaches 0 of y is going to be the limit as x approaches 0 of the natural log of sine of x to the 1 over x power. So basically, we're taking the limit of the natural log. We're going to get some answer, but then our final answer isn't going to be what y is equal to. It's going to be what e to the y is equal to. So we're going to undo the natural log at the end. So same kind of process. We don't have a fraction yet, right? I don't have 0 over 0 or infinity over infinity. I have the natural log of 0 to the infinitieth power. That seems terrible. Yeah. I feel like I didn't list that one as one of my, I feel like I might have gotten it backwards there. Sorry. So then we're going to bring down the 1 over x in front times the natural log of sine of x. And really here, I kind of already have the quotient. I just didn't write it that way. I should really have written this as the limit as x approaches 0 of the natural log of sine of x over over x. And there's a reason I didn't write this as one of my indeterminate forms, because it's not. So if I plug in 0 right now, what do I actually get? Which I know is a hard question. Well, sine of 0 is 0, so I'm getting the natural log of 0 over 0. Well, the natural log of 0 goes to negative infinity. And a really big number divided by a really small number still stays really big. This is just negative infinity, which means that this limit here is going to be e to the negative infinity, which is 1 over e to the infinity, which is 0. Which you probably could have justified to yourself by saying, well, look, I have something that's really, really small, raised, so small being smaller than 1 specifically, have to be smaller than 1, like just not getting close to 1, getting closer to 0 or a half or something that's distinctly not 1. If you take a number that's smaller than 1 and raise it to a really big power, you're essentially saying a small number times a small number times a small number times a small number over and over and over again. It's going to be closer and closer to 0. So I will point out that this expression here, which is like a 0 to the infinity, this is not indeterminate, or it is already determined, and it's going to be 0. Right? 0 times itself a bunch of times, 0. That doesn't show what I want to show, so let's do the other. What I wanted was infinity to the 0. Yeah, sure. We can squeeze in one more problem. The limit as x approaches infinity of 2x to the 1 over x. Here's an infinity to the zeroth problem. And here's where I would say instead, let's look at the limit as x goes to infinity of the natural log of 2x to the 1 over x. And then we can bring the exponent down. It's a limit as x goes to infinity. I should skip this step, or I should be smarter about rewriting it and write it as the limit as x goes to infinity of the natural log of 2x over x. And now it definitely is a limit where we can use L'Hopital's rule. So using L'Hopital's rule, since it's an infinity over infinity type, I get the derivative of the top, which is 1 over 2x times 2, and the derivative of the bottom, which is 1. That's going to be the limit as x goes to infinity of 1 over x, which is 0. And this is where it's really, really easy to forget that there's something else to do. Our answer isn't 0, because we looked at the limit of the natural log of this expression. So this is equal to the limit as x goes to infinity of e to the natural log of 2x to the 1 over x. And we just figured out that the part that's in bracketed there, that the part that's in brackets there, the limit of that part is 0. So our answer is going to be e to the 0, which is 1. That's why I don't love doing it this way, because I think it's easy to forget to do that last part where you go back and do e to whatever your answer was. But you should do whatever you like, what your professor has told you to do, obviously. Yeah. There's more to be said about L'Hopital's rule, but that covers most of it. I mean, there's always more to be said about all the topics, really. Yeah. So that's kind of it. No class on Thursday. Good luck on your finals. As in case you weren't aware, I will be gone tomorrow, Thursday, and Friday, but I will be around next week during finals week. All my office hours, I posted them on Canvas. They're all going to be in the library on the lower level where all the student tutors are. You're welcome to send me a message if you have any questions. I'll try to find some relevant videos for any other content that we might have want. Like, we covered most of the content. I feel like there's a few other things we could have said. So I'll see if I have some older videos that still would be worth watching. You obviously don't have to watch them, but I'll post them there for you. And I'll see if I can find some relevant content, like final exam review / practice finals to post as well. And I'll definitely try to post the practice finals for each classes, although I feel like the people in Chan's class probably don't need to look at the practice final for this class, because it just feels like his is, his just seems like it's a little more extreme than the other. So good luck. I hope your finals go well, and I hope I see you all next quarter in Co-21B, which I'll be teaching. I should post something. I'll post something on Canvas about that too, about when and where it is. But it's also on our website, right? So this should be listed on the AATC website, tutoring.ucdavis.edu. I think it's Tuesday, Thursday. It's either from 12 to 1:30 or from 3 to 4:30. One of those two times. Good luck on all your finals. Oh, and the best piece of advice I can give you, make sure you read the questions on your exam slowly and carefully. I promise you it'll save you time. So do that. And good luck. Yeah, you're welcome. Yeah, you too. Appreciate it. You're good.
I was wondering for the Math 21B for next quarter, will it be a CRN on the website? Or
Yeah. So well, you can do so. I'll put so either way you want to do it. You can either sign up for the CRM, which that means your attendance is required, you fill out the form, or you can just get added to Canvas eventually. Like, because I don't have the Canvas set up yet. And just it's less restrictive in that way. So if you need a unit, you just have for the CRN. If you don't need a unit, either way is fine.
That's good. All right, thank you.
You're welcome.